Now we're going to look at conditional probabilities. Part of introducing conditional probabilities, we want to introduce what an independent versus a dependent event is. And so for two outcomes to be independent, that means that one does not influence the other. For two to be dependent, one influences, or one outcome influences the other. So the fact that one already happened changes the likelihood of the other one happening. Two examples for that, we have gender versus pizza. You know, everyone loves pizza, or at least maybe 95% of the people, and that's regardless of whether you're male or female. So we would think that if someone loves pizza, is independent of their gender. On the other hand, when we're looking at gender versus pink shirt, we would assume that females are more likely to own a pink shirt. Not to say that males don't own pink shirts, but they're just more likely. So the percentages are going to be different, meaning that if we already know that the person is male, we're going to know that they have a lower probability. So with that, we can look at independent events, and we can say that the probability of A given B, which is the conditional probability of A given that B already happened, is equal to the probability of A if A and B are independent. Because we already said the fact that B already happened does not affect the probability of A over here. Or the same thing in reverse, the probability of B given that A already happened is equal to the probability of B. So if you're rolling a dice and you're rolling another dice, one outcome does not influence the other. They're independent. Same thing with tossing a coin. So let's say you tossed a coin and you had a head and a head and a head and another head, and you're going to say, hey, I must be due for a tail. What is the probability of having a tail on the next one? Well, it's actually the same as having the probability of a head. So just because heads already happened 4 times doesn't mean that we're due for tails, because the probability of tossing a tail is always 1/2 or 0.5. So this is what we call independent. Let's look at our examples from the beginning of the section. This is where we roll 2 dice. So consider our events from before, where A was having a sum of 7 and B was doubles and C was a sum to 10. We have 2 things we defined. We defined joint versus disjoint. Remember when we're looking at a Venn diagram? Disjoint would mean there's no overlap, where joint would mean that they do have an overlap, right? So this is joint versus disjoint. Disjoint means they cannot happen at the same time. For example, when we're looking at having a sum of 7 and doubles, could we have that happen at the same time? No, that's not possible. Therefore, we have A and B are disjoint. Could we have doubles and sum of 10 at the same time? Yes, that's possible, because we could have a 5 and a 5 that would add up to 10. So B and C are joint, because 5, 5 is in both events, right? That's our overlap. And then could we have a sum to 7 and a sum to 10? No, that's not possible. So A and C are also disjoint. So oftentimes people confuse joint, disjoint with independent and dependent. So remember, independent and dependent is a little different. This is looking at the fact that one already happened. Does that change the probability of the other one? Well, let's look. Let's look at the probability of A given B. So this is the probability that we already have doubles, right? Given that we have doubles, what is the probability that we have a sum of 7? Well, the probability of having a sum of 7 is equal to 0, which is not equal to the probability of A, which was 1/6. So we already can tell that A and B are dependent. Let's continue on with the next two events. So let's see the probability of A given C. So over here we already know that the sum is 10. What's the probability of the sum being 7? Just like before, this is equal to 0. It's not possible, which is not equal to the probability of A. And therefore we have A and C also dependent. Let's check the last one, and we knew that B and C had some overlap, so this one, let's look a little closer at that. So the probability of B given C, so we already know that the sum is 10, and therefore we want to know what's the probability that we have doubles. So when we looked at the sum of 10, remember we had the different events 4, 6, 5, 5, and 6, 4. So given that the sum is 10, meaning we're only inside those three events, what is the probability that we have doubles? Well, that would be a 1 in 3 chance, because one outcome out of our 3 outcomes is equal to doubles over here. So we have a 1 in 3 chance. Now this is not equal to the probability of B, because the probability of B was the probability of doubles, which we had the events 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. Which was a 1 in 6, or 6 out of 36 chance. So B and C are also dependent. And now we've checked all the pairs. One more event to look over here is consider 2 new events. D is the first die rolled is a 3. And E is the second die rolled, shows a 4. So we're rolling 2 dice. Which best describes these 2 events? So these are a little different compared to the previous ones. We are rolling these dice independent. We're not summing them up or looking at, the different outcomes when we're adding them, or when we're looking at doubles. We're simply going to observe the first roll, observe the second roll, and then look at, what's the chance of having the first one be a 3? What's the chance of having the second one be a 4? So could that happen at the same time? Meaning, is this joint? Yes, because we could have a 3 on the first one and we could have a 4 on the second one. Therefore, this is joint. Now, is it dependent or independent? Does the first roll affect our second roll? And our die doesn't have a memory or anything, so our rolls are independent. So we're going to say joint and independent, which is option C over here. So keep in mind, look at the question very carefully. See if they could happen at the same time. If they do, then they're joint. If they cannot happen at the same time, then they're disjoint. And if one does not affect the other, then we call it independent. If the one affects the other, meaning we already know one happened, will that change the probability of the other one happening? Then it's dependent. So these usually are really difficult for students, especially to see the difference between disjoint, joint, and dependent and independent. So one last question over here is looking at voter registration. The first event is voter is registered as a Democrat. The second one is voter is registered as a Republican. And we're just looking at one voter. So looking at whether the person could be registered Democrat and Republican at the same time. And the answer is no. Therefore, it is disjoint. So yes, because it cannot happen at the same time. So just looking at one person. Are these independent? So the fact that we know that a person is a Republican, will that change the probability that he's also a Democrat? Yes, because we already said that we're looking at one person. They can only be registered Democrat or a Republican. Therefore, this is equal to 0, which is not equal to the probability of the person being Democrat. So we know that it is disjoint as well as dependent.